Okay, so hello everyone. In this video, we will cover routing protocols. So, in this video, we will discuss introduction to routing protocols, then distance vector routing (DVR), then count to infinity problem, and at last, we will discuss link state routing. Although, don't worry about these complex names; these are so simple topics. What is a routing protocol and what are its different categories? We are going to discuss in detail. But before that, I want to tell you about the major functionality of network layer, which is forwarding. Forwarding means to put the packet on the right path. The right path should be the optimal path, okay, meaning the shortest path with lesser delay and cost, so that the packet reaches quickly. Basically, who does forwarding? The router. Okay, a router is generally connected to multiple networking networks. Let's say a router is connected to n1, n2, n3 and n4 multiple networks. Okay, now when any packet arrives, the packet is received by the router. After receiving the packet, it will open the packet internally and send it to the right path. So how should a router find out whether to send it to n1, n2, n3 or n4? The answer is through routing tables. Now, what is routing table? It is a collection of entries that contains information about what is happening inside the complete network. All the values in the network are connected in the routing table. It provides information about which connection is working, which connection is not working, from which network to which other network the packet has to go, and what is the cost. All these details are maintained in the routing table. Now, how is a routing table created? To properly create a routing table, either we can make a static routing table or dynamic one. What is static one? Okay, static routing table means it is created manually. You have to manually insert data in the routing table. Who has to do it? The network administrator. This is possible in a small network where you can manually enter the data. But if we talk about the internet, everything is dynamic. Rather than using static routing, we work on dynamic routing. Our routing tables should automatically exchange information with each other and be automatically updated. So, how is a dynamic routing table created? To make them, we use routing protocols. These are set of instruction and rules which helps router to share data and update their routing tables, okay, from time to time. Because when any packet comes, that packet on the basis of the routing table can be checked for the direction in which it should be sent. Now, types of routing protocols. The routing protocols that we have can be categorized into different types: intra-domain and inter-domain. Okay, as we all know, the internet is a very big network. What we call this complete network is the internet. But internally, we have divided the internet into autonomous system. An autonomous system is a collection of different networks that are connected to each other and under one particular network administration. Okay, for example, if we talk about Delhi and all the computer networks under Delhi, all the small networks, after connecting them together, the complete Delhi network could be called an autonomous system. Okay, similarly, Mumbai also has its own autonomous system. Okay, now inter-domain routing is how communication occurs between different autonomous system. This is when one autonomous system want to communicate with another autonomous system. This is inter-domain routing. Now, what is intra-domain? Intra-domain routing is within one autonomous system. Okay, for example, if I want to send information from Hoj Khas to Green Park within Delhi, so we are doing routing within an autonomous system. Okay, different routers within the autonomous system want to share data about cost, which links are running, which links are not working. All this stations is shared with the help of intra-domain routing. Under intra-domain routing, we have distance vector and link state routing. For distance vector implementation, we use RIP, routing information protocol, a real life protocol that we generally use to share information in intra-domain routing. Similarly, there is a OSPF, open shortest path first, okay, which works on link state routing. For inter-domain, we have BGP, border gateway protocol, which works on path vector routing. If you are preparing for GATE, NET or any kind of exam, remember that distance vector is the most important algorithm. Okay, all three protocols works on unicasting, meaning one-to-one communication, where one person wants to send data to another person. Okay, this is unicasting. This is the basic information about routing protocols. Next, we will discuss one by one what is distance vector routing protocol, link state routing, count to infinity problem. These we will discuss in this video. Now, first comes distance vector routing, DVR. Now we are going to discuss distance vector routing, which is an intra-domain routing protocol. Intra-domain means all the router inside the autonomous system will share information with the help of DVR. Okay, in this diagram I have taken N1, N2, N3, N4 and N5. These are routers connected with links. Okay, our main purpose is that the routers will share information about the network so that they remain updated. This helps in forwarding the packet. Now, when I want to route a packet, I have to find the minimum distance or shortest distance. But if I don't have information about the complete network, how will I find whom to send next? For this, we use distance vector routing, where routers share information among themselves. Now, DVR working mechanism. Each router maintains its routing table. The routing table in DVR has three components: destination, distance, and next hop. Destination, which destination node this is. Distance, this can be considered as the cost or propagation delay or number of hops. So this is distance column, distance vector column. And the third one is next hop, means through which router it has to go. Let me explain with the network where we have cost n1 to n2 is 1, n2 to n3 is 6, n2 to n5 is 3, n3 to n4 is 2, n4 to n5 is 4. Now what is initial local routing tables? The first rule in distance vector routing is that all the routers in the network should know how many routers are present in the total network. Every router knows there are 5 routers in the network. The second point is that we use hello messages to discover neighbor nodes. N4 will know its neighbor, okay, n5 will know its neighbors, and so on. Okay, now let's start with n1's initial routing table. From n1 to n1, what is the distance? 0. And what is the next hop? n1. From n1 to n2, the distance is 1. Next we will reach n2, direct connection. This is a direct connection. From n1 to n3, we want to go from n1 to n3. What is the distance now? We don't know, so this will be infinite. So the next hop will be, we don't know, okay, no direct connection. Similar for n3, n4, n5. Okay, from n1 to n4, distance is also infinite, and next hop we don't know. From n1 to n5, distance is infinite, and next hop we don't know. Now similarly for n2's initial routing table, from n2 to n1, distance is 1. Next hop we will reach n1. From n2 to n2, distance is 0, and next hop will be n2. And from n2 to n3, distance is 6, and next hop is n3. From n2 to n4, distance is infinite because we don't have a direct connection, and next hop we will don't know. Okay, from n2 to n5, distance is 3, and next is n5. Now for n3 initial routing table, n3 to n1, distance is infinite. Okay, next hop we don't know. n3 to n2, distance is 6. Next hop we will reach n2. Okay, n3 to n3, distance is 0. Next hop we will reach n3. n3 to n4, distance is 2. Next hop we will reach n4. Okay, from n3 to n5, distance is infinite, and next hop we don't know. Similarly for n4 initial routing table, n4 to n4, distance is infinite. n4 to n2, distance is infinite. Okay, n4 to n3, distance is 2. n4 to n4, distance is 0. n4 to n5, distance is 4. Okay, and next hop we will reach n3, n4, and n5. Okay, for n5's initial routing table, from n5 to n1, distance will be infinite because there is a no direct connection, and next hop we will don't know. n5 to n2, there is a direct connection, distance will be 3. Okay, next hop we will reach n2. Okay, n5 to n3, distance is infinite. n5 to n4, distance is 4. n5 to n5, distance is 0. After forming local routing tables, these are local routing tables, okay, these are not final tables. After forming local routing tables, the distance vector has to be shared. There are two very important points you have to consider. The first point is share only with neighbors, okay, not with everyone. This is the distance vector sharing, share only with neighbors nodes. So the first rule is share only with neighbor nodes, not with everyone. And the second very important rule is share only the distance vector. We have three fields in matrix: distance vector, next hop, and the distance. So we will share only distance vector. So share only the distance vector, not the complete routing table. The table we have formed, we will not share the entire table, we will only share distance vector to our neighbor nodes. These are two important points you have to consider in distance vector routing. Distance vector means only the distance column values. For example, n1 will send 0, 1, and infinite to n2. This saves bandwidth because we are not sharing the complete routing table. n1 shares with n2 only, n2 shares with n1, n3, and n5 only. Okay, and n3 shares with n2 and n4. Okay, and n4 shares with n3 and n5 also, and n5 shares with n2 and n4 also. So these are their neighbors. Now time to updating our routing tables. Let's see how n1 updates its routing table after receiving n2's distance vector. What is n2's distance vector? 1, 0, 6, infinite, and 3. This is n2's distance vector. Now we will only see the new distance vector. We will don't see the old table we have formed. So for updating n1's routing table, what it will be? n1 to n1, distance is 0. Next hop is n1, unchanged. Okay, this entry is unchanged. Now n1 to n2, there is direct link, so distance will be 1, and next hop will be same, n2. The n2 shared distance vector 1, 0, 6, infinite, and 3. So from n2 to n3, what is the cost or what is the distance? 6. To reach n1 to n3, we have to go through n2. Okay, so you can see it like, first we will go n1 to n2, and then we will go n2 to n3. So n1 to n2 cost 1 plus n2 through n3 cost 6. We have seen our new distance vector. Okay, this will be 7. So next hop will be n2 via n2. We are going n3 via n2. So n1 to n4, what is the distance? We have to first go to n1 to n2 and then n2 to n4. So for n1 to n2, what is the cost? 1. And for n2 to n4, what is the cost? Infinite. So it will become infinite also. Next hop we don't know. Okay, from n1 to n5, what do we have to do? We have to go to n1 to n2, then we have to go to n5, n2 to n5. Okay, so what is the cost of n1 to n2? This will be 1. And what is the cost of n2 to n5? This will be 3. Total distance become 4. n1 to n5 distance is 4. And next of n2 via n2, we have used our new distance vector, n2's distance vector. N2 has shared with its neighbor. So this is the updated routing table of n1. The key principle is old routing table is never used. Okay, let's also see n5's update after receiving distance vector from n2 and n4. Okay, n2's distance vector is 1 0 6 infinite and 3, and n4's distance vector is infinite infinite 2 0 and 4. Okay, for n5 to n1 via n2, this is there is distance is 3 plus 1, which is equal to 4, and via n4 this is equal to 4 plus infinite, so infinite. So we will take for minimum distance, so minimum distance is 4. Okay, and next hope we will reach n2. For n5 to n3 via n2, the distance is 3 plus 6 equal to 9, and via n4 there is 4 plus 2, the distance is 6. So we will use minimum distance 6. Okay, so next hop will be n4. So that's how we will create n5's routing table. Okay, this process continues for multiple passes until all routing table coverage to optimal values. Okay, after 3-4 passes you will get finalized routing table with minimum distances. The beauty of distance vector routing is that information propagates through the network gradually. Okay, in the first pass n1's information reaches n2, in the second pass n1's information reaches n5, in third pass n1's information reaches n4, and so on. These updates keep happening because changes can occur anytime in the networks. Links may break. Okay, now there is a problem in distance vector routing. What is the problem? Count to infinity problem. We have solved this in today's era, but there is a problem called count to infinity problem. Okay, now I will explain the count to infinity problem in distance vector routing. Okay, this problem occurs in distance vector routing due to some specific reason. Let me take an example. Consider a simple network with nodes A, B, and C, and internet connection. You can see it on screen also. What is the normal case? Initially, we have node A connected to node B. Okay, what is the cost? Cost is 1, and internet cost is also 1. Okay, node C connected to node A, cost is also 1. So initially B's cost to reach internet is 1, direct connection. Okay, A's cost to reach internet infinite, because A doesn't have an direct connection to internet. Okay, so it will be infinite, doesn't know initially. Okay, C's cost to reach internet, it will be infinite. Okay, after first pass B tells A that I can take you to the internet at cost of 1. Now A will calculate that cost to B is 1 and B's cost to internet is 1. So A will change its value to 2, infinite to 2. Okay, so A's cost to internet becomes 2. After second pass, A tells C I can take you to the internet at cost 2. Okay, so C calculate cost to A is 1. Okay, A's cost to internet is 2. Okay, so total cost is 3. So C's cost to internet becomes 3. In subsequent passes, these values stabilize because no better paths are found. Okay, this is normal operation. Now what is count to infinity problem? Now let's say the link from B to internet breaks. B immediately knows this and set its cost to internet as infinite. Here's where the problem occurs. Now let's understand what is the count to infinity problem after link break. Okay, the first round after link break is B sends to A that my cost to internet is infinite, but C sends to A that I can take you to the cost of 3. A receives both messages. B can't take me to infinite cost, but C can take me at cost of 3. So A calculate recosted. So cost to C is 1 and plus C's cost to internet is 3. So total A updates its cost to internet as 4. Okay, but here is the crucial issue. C doesn't know that its path to internet goes through A, and A doesn't know that C's path goes through A. But this is because in distance vector routing, router only share the cost values, not the path information. We have already discussed. We are sending only distance vector column, not entire table. Okay, Meanwhile, A also sent to B. A tells B, I can take you to the internet at cost 2, okay, using old information. Okay, B calculates cost to A is 1 and A's cost to internet is 2. Okay, so B update its cost to internet as 3. Now in second round, B tells A, I can take you to the internet at cost 3. Okay, so A calculate cost to B is 1, B's cost to internet is 3. So total cost is A's cost remain 4. Okay, so A tells C, I can take you to the internet at cost 4. Okay, so C calculates that cost to A is 1 and A's cost to internet is 4. So C update its cost to internet as 5. After third round, C tells A that I can take you to the internet at cost 5. A calculates cost to C equal to 1 and C's cost to internet is 5. Okay, so A update is cost to internet as 6. A tells B that I can take you the internet to the cost at 6. Okay, B calculates cost to A is 1 and A's cost to internet is 6. So it will become 7. Okay, B update its cost to internet as 7. Okay, so this process continues with cost increasing 4, 5, 6, 7, 8, 9 and so on. Okay, and can theoretically reach infinity. This is called the count to infinity problem. The root cause is that routers only share distance values, not path information. If they shared path information like I reach internet through you, this problem would not occur. Okay, this problem was later resolved through techniques like split horizon, but initially this was a significant issue with distance vector routing algorithm. So we have solved this problem in link state routing. Now I am going to explain link state routing. Okay, moving forward to link state routing. Link state routing is another intra-domain routing protocol different from distance vector routing. Okay, in this example we have 6 router R1, R2, R3, R4, R5 and R6, okay, connected to each other with given cost. We use link state routing so that router can make their routing tables and update them regularly. Okay, the routers we have in link state routing initially make their link state table. Okay, link means the edge connections, state means whether the link is up or down, whether the link is running or not. Now what is the step 1? Step 1 is creating link state tables. Each router sends hello message to discover its neighbors and creates its link tables. Okay, for example, R1's link state table is what? Connected to R2 at distance 6, connected to R3 at distance 3. This is the R1's link state table. And what does it contain? Extra values, sequence number and TTL fields are also included. TTL fields, and I have explained it in our previous lectures, you can check it out. Now what is R3's link state table? R3's link state table is connected to R1 with distance 3, connected to R2 is distance 2, connected to R5 with distance 9. Okay, this is R3's link state table. What is R5's link state table? Connected to R3 at distance 9, connected to R4 is distance 1, R6 at distance 4. Okay, notice that link state packets contain more information than distance vector. They include sequence number, usually 32 bits, and TTL field. Okay, time to live fields. Okay, this means more bandwidth utilization compared to distance vector. Now step 2 is flooding. Okay, the major difference from distance vector routing is that in link state routing we use flooding instead of sharing only with neighbors. Okay, flooding means R2 or R1 will send its link state packet to everyone in the network. Okay, not just neighbors or everyone to the network. Okay, this provides reliability because if R1 floods, packets will reach destination through multiple paths. Okay, even if a packet is lost, if it will reach by another path. Flooding uses more bandwidth and create more congestion because we are sending packets through multiple routes to everyone in the network. Now what is step 3? Building complete network database. Okay, after flooding, each router receives link state table from all the routers. Okay, for example, R1 will receive link state table from R2, R3, R4, R5 and R6. Okay, from these received table, R1 builds its complete network base. R1 knows it's connected to R2, distance is 6, and R3 distance is 3. So from R3's table, R3 is connected to R5, distance is 9. Okay, from R5's table, R5 is connected to R4. Okay, distance is 1, and R6 distance is 4. From R2's table, R2 is connected to R4, distance is 7. From R4's table, R4 is connected to R6, distance is 8. Okay, this gives R1 global knowledge of entire network topology. Now what is step 4? Applying Dijkstra algorithm. Now R1 uses Dijkstra algorithm, single source shortest path, to find the shortest distance to reach all the routers. Starting from R1 to R2, initially it is 6, direct link. Okay, R1 to R3, initially it's 3, direct link. Okay, now from R1 to R4, R5, R6, initially infinite. Okay, now after first iteration, select R3. Okay, minimum distance is 3. R1 to R2, minimum distance is 6 plus 3 plus 2. This become 5. Okay, the minimum value will become 5. So via R3, R1 will go to R2. So R1 shares via R3 with the cost of 5. Okay, R1 to R2 cost is 6. Okay, we will take the minimum. This is the Dijkstra algorithm. Okay, R1 to R5, 3 plus 9 equal to 12, okay, via R3. Now in second iteration select R2, minimum distance is 5, okay. Now we have to calculate R1 to R4, okay. Minimum is infinite from R1 to R4, but if we are calculating via R2, means it will become 5 plus 7 equal to 12 via R2, okay. So after second iteration R1 to R4 it will become 12, okay. Minimum distance is 12, okay. Now what is third iteration? Third iteration is select R4, okay. Minimum distance is 12, R1 to R6 will become 12 plus 8 equal to 20 via R4, okay. R1 will go to R4 and then R6, okay. After fourth iteration select R5, okay. Minimum distance is 12, okay. R1 to R6 minimum is 20, but 12 plus 4 via R5 is it's 16, okay. So it will take 16. Now what will become the final routing table for R1? Destination, distance and via, okay. So destination is R1, distance is 0 and via R1, okay. Now destination is R2, distance is 5 via R3, okay. R1 is going to R2 with distance of 5 via R3, okay. This is the meaning of this table, okay. Now R1 is going to R3 with the distance of 3 via R3. R1 is going to R4 with the distance of 12 via R3. R1 is going to R5 with the distance of 12 via R3, okay. R1 is going to R6 with the distance of 16 via R3. So similarly every other router will create its own routing table using the same process, okay. Now what is the key differences from distance vector? Information sharing. Distance vector shares only with the neighbors, okay, but link state floats to everyone. Now knowledge. Distance vector has limited knowledge, link state has global knowledge. Algorithm. Distance vector uses Bellman 4, link state uses Dijkstra. Bandwidth. Distance vector uses less bandwidth, but link state uses more due to flooding, okay. And convergence, okay. Link state converges faster due to global knowledge, okay. Reliability. Link state is more reliable due to flooding. So this completes our discussion on routing protocols: distance vector routing, count to infinity problem, and link state routing. So that's it for this video. We will meet in next video. Until then, bye bye.